Right, now we're going to move on and look at the annuity. So we'll see a slightly more significant piece of notation, arguably, which is the life annuity notation. That double dot X means the present value of a payment of £1 at the start of this year and the start of every year for the remainder of the life of somebody who is currently aged X. Okay, so the the small a is for annuity, a large A means assurance, X is the age, and the double dot means due, which is the posh word for at the start of the year. Okay, so what is the value of AX? Well, if you're going to get a payment of £1 at the start of the year, let's sort of go straight to the algebra here. Okay, if you're going to get a payment of £1 at the start of the first year, then you're bound to get it. Okay, so there's no probability of you not getting it, and also there's no discount for time in the future. Okay, so that is worth 1. Okay, let's assume here that the rate of interest is I%. Okay, and we're going to remember that V is equal to 1 over 1 plus I. So we're going to use our V now. Culturally, we don't get delta and F and all sorts of things involved here. We're just in that world where we assume a constant rate of interest. We pick our rate of interest and we use that rate of interest. Okay, so we're assuming a flat yield curve. Okay, which is one of the things that causes confusion. So we'd probably, if we wanted to talk about the force of interest, we would probably use delta rather than F or S or something like that, or R. But it's just a cultural thing that the two areas of math tend to happen in different places, and therefore they've developed different symbols, which makes it a bit confusing. So here we would tend to use I for the rate of interest, the annual rate of interest. V is 1 over 1 plus I. V is always 1 over 1 plus I. If we wanted to get involved with the force of interest, we don't really need to, because things tend to be annualized. And the reason for that is we've only got the tables which are annualized. So the real world actuarial tables are genuinely just annualized numbers. Okay, so we tend to deal with discrete annualized mathematics and then adjust for that where we've got other things going on. So the world of variable yield curves and sloping yield curves is kind of a different world at the moment. Okay, so putting that aside, okay, the value of this annuity is 1 plus, what's the value of next year's payment? Well, next year's payment is going to be 1, but you're only going to get that payment if you survive. Okay, so times by, what's the probability of surviving 1 year? 1px. But it's in a year's time, so we've got a discount to calculate the present value. A pound in a year is not worth as much as a pound now, so we discount by 1 over 1 plus I, but we're calling that V in this case. Sorry. Okay, then what about 2 years? Plus 1 times 2px times v squared. See how it's working? Plus 1 times 3px times v cubed. And it goes on forever. Okay, eventually these values will be 0. So by the time that's 100, they'll basically be 0. And most actuarial tables run out at about 100. And if you're age 65 at this point, it's going to run out after about 35 years. Okay, but that is the formula for an annuity. Okay, and you can look those up in your tables. So you should have red tables now. You used to have orange tables. When I did it, there were green tables. But these are the numbers that are actually tabulated. Okay, so you'll have in your actuarial tables, you'll have X, 0, 1, 2, you'll have LX, which typically is 100,000, the first one, then 99, 500, something, And then you'll also have a double dot x, and it will be at a particular rate of interest, say 4%. So if it's 4%, I can tell you that is about 25. And in fact, most of these are about 25, because most of what's going on if you've got a 4% interest is it's the interest rate that's actually controlling the value, because by the time you get to 100, it doesn't really matter whether you die or not, because the value has gone down so low. So it might be 24.9, 24.8, just sort of guessing those numbers. But those numbers are given in the tables because, okay, to work this out, you've got to calculate, you've got to do that calc, that calc, that calc. And you can't do all that. You can do it on a spreadsheet, but you can't do it all in an exam. So you are given these numbers. The skill then is to deal with different scenarios. Okay, so you might have a temporary annuity, you might have a deferred annuity, you might have an annuity payable halfway through the year. Okay, so that's where we get into a slightly more complicated issue, and the main, perhaps the central issue we can deal with is the term annuity, which stops after a certain period of time, because that really illustrates all the concepts. So our next piece of notation is going to be a double dot x colon n and that angle bracket. Okay, and that is the same sort of thing. Okay, again, that means due, that means annuity, that is your age. Okay, but that is the term. Okay, so there are only n terms. Okay, so you're only going to get this payment for n years. Okay, so let's, and it's a bit similar to where we did a term annuity where there was no, where we did the sum equals alpha over 1 minus rho, and then we chop off the part at the end. Okay, we can do a similar sort of thing here. Okay, so what this is going to be, let's get a white pen, a x n equals 1 plus 1 p x dot v plus, but v squared is probably more normal convention, 2px, I was going to miss the 1's out, plus v to the n minus 1, okay, because that is the nth payment, times n minus 1 px. Okay, we don't have a, if we had a table, okay, for AXN, again we need a two-dimensional table. We need a row, a column of x's, say, and a row of n's. But if we're clever, what we can do is realize that what this is an infinite annuity minus a deferred annuity. So we're sort of taking off. So at this point, we're kind of taking off v to the n npx plus v to the n plus 1 n plus n plus 1 px. Okay, so that's what we're effectively doing. This annuity here is a whole of life annuity minus this annuity here. So what we can do, okay, is work out, have we got an expression for this? So let's move that up there, and let's try and understand what this expression is here. So v to the n npx plus v to the n plus 1 n plus 1 px plus, let's just keep going to really make it nice and simple. V to the n plus 2, n plus 2 px. Okay, what I'm going to do is take this out as a factor, because what I want to be able to do is take off something that looks like a whole of life annuity. Well, the whole of life annuity starts with a 1. Okay, so I want this to start with a 1. Okay, plus da da da, plus da da da. Okay, plus etc. I want that to start with 1. So what I'm going to do is take out a factor of v to the n npx. Okay, well then v to the n npx, take out a factor of v to the n npx, I get 1. What do I get if I take a factor of v to the n npx out of this thing? Well, that, the v to the n goes to v, and then this is the probability a life aged x survives for n plus 1 years. This is the probability that a life aged x survives for n years. Well, the chance of a life aged x surviving for n plus 1 years is the chance we survive for n years, followed by the probability a life aged x plus n survives for 1 year. Okay, so that is times 1 p x plus n. Okay, so if you think about that carefully, all you're doing, multiply that by that and you get that. Fairly obvious for the v, but for the probability, so if you're at age x, if you're age 40 to survive to 51, you've got the probability that a 40-year-old survives to 50 times by the probability that a 50-year-old survives to 51. Okay, so the next one then, factor that out, v squared times 2p x plus n, and so on. And then what is this expression? 1 plus v times 1p x plus n plus v squared times 2 x plus n. Well, if you notice, that is the same as this expression, only instead of having an x, okay, we have an x up there, here we have an x plus n. Okay, so this expression is equal to v to the n npx times by a double dot x plus n. Okay, that is the thing we've chopped off at the end to convert the whole of life annuity that we had here into the temporary annuity we had here. So we get one of our most important and most useful formulas, which we'll do in a different colour. Let's do it in pink. We get the annuity to life age x for n years, that's a colon, is equal to the whole of life annuity to life age x minus v to the n times n p x times a double dot x plus n. Okay, and that is what we call the annuity partition, or it's what I call the annuity partition, because that enables us now to calculate the annuity for any value x and any value n with just a one-dimensional table of ax's. You think about it, I've got my table I need to look up only has the one parameter x there, and it only has the one parameter there. I don't need x and n, because I'm doing x is 40 and n is 10. I just need to look up the one-dimensional table at A40 and the one-dimensional table at A50. Okay, so that is one of the most sort of key formulas in actuarial maths, and we'll go on to do how we adjust for that when things are non-integral. But the most difficult part of that is where we don't pay we don't pay every year, we pay every month or every 6 months or stuff like that. It's fairly easy, and I'll just do this now. It's fairly easy to deal with the situation where x is not an integer because you just do linear interpolation. Okay, so if we have let's go back to white. So if you wanted to work out a a 65.2 for 10 years, okay, all you do is interpolate. So you've got some A65 for 10 years and you've got some A66 for 10 years. It's closer to 65, so that one will be 0.8 and that one will be 0.2. If you want, you could do that geometrically as well. Wouldn't make very much difference because over a small intervals they are very close to linear anyway. Okay, so but that's how we deal with that not being an integer. And then the more complicated part, which we come on to in a different section because it is more complicated, is how we deal with it, say, being a monthly or a weekly payment, and that's in this section here, m minus 1 over 2m. But we'll do that in a later edition.